Good morning, everyone. Good morning. Hope all is well. Hope everything is all right. Hope you had a great weekend. All right. So we're looking at our last class. We did a test. Anybody have any questions on anything? Anybody trying to think, get stuck on any problems before we get rolling? Yep, not a problem. Not a problem. Just stay back and we'll make sure you're straight. All right. So let's see where we left off. This MD60. Let me go back here. Got multiplying polynomials. This is where we left off, if I'm not mistaken. I think last class, and you guys can let me know if I'm mistaken. I believe or did we need to multiply polynomials? Anybody remember? So I think we added and subtracted already, and we need to multiply polynomials. All right, I think we are here at 12. Nope, hold on. Adding.
The last one that we did was polynomials 12.2.
Thank you. Okay. All right. So I'm just trying to get that confirmation. I appreciate that. So yeah, because last class we didn't do anything, so out of my flow. Okay, so we're here at 12.3. Appreciate that once again. Multiplying polynomials. So last time we had a lecture, it was adding and subtracting polynomials, which was 12.2. I'll put the wrong thing. Which was 12.2. So now we're looking at multiplying polynomials, which is 12.3. Got a few people trying to come in. There we go. Okay, so when we look at multiplying polynomials, we're going to hold true to our polynomial rules, our exponent rules. And even if you don't write it out like this is how you should be processing it. In other words, you're going to take 3, we have 3x to the 4th times 4x squared. So we're going to take 3 multiplied times 4, and then x to the 4th multiplied times x to the 2nd. So the 3 times 4 is 12. And then here, your exponents, don't forget, whenever you are multiplying your variables, you're going to add your exponents. So that 4 plus 2 will give us a 6. And so that's the foundation of multiplying your exponents.
It's multiplying the like terms pretty much.
Yes, sir. Yep. Or like variables. Yeah. So when we look at that next one right here, -4 c to the 5th d times 2c squared d cubed e. And we're doing just like your classmate suggested, pretty much multiplying your like variables. -4 times 2 c to the 5th times c squared d times d cubed, and then e sitting on the outside with nothing to simplify with. -4 times 2 is 8. 5 plus 2, your exponents is 7. And then 1 plus 3. Remember, if you don't see anything, they assume you know there's a 1 there. So 1 plus 3 is 4 for the exponent of d. All right. Any problems? Any problems?
Why is the C 7 instead of 10?
Oh, you add your exponents.
Okay.
Mhm.
Okay.
Yep. Whenever you multiply your variables, your like variables, you add your exponents.
Okay. Appreciate that.
Mm-hmm. All right, and I scroll up. Very good. Okay, so the next one, instead of just single terms, we have a single term multiplied by two terms. You know, your minus and plus signs will separate your terms. So we have 2x times this quantity of 4x minus 3. So won't necessarily write it out like this every single time that we do our distribution, but this is the visual on it. 2x times 4x and then 2x times 3. So here, 2x times 4x, 2 times 4 is 8, x times x, x squared. Then 2x times 3 is 6x. All right, next one is negative 3a squared minus 4a squared plus 2a minus 1. So just like we distributed the 2x in the first one, here we will distribute negative 3a squared. So don't forget to distribute the negative along with your 3a squared. So negative 3a squared times negative 4a squared. So negative 3 times negative 4 is a positive 12. A squared and a squared, a to the 4. Negative 3a squared times 2a. Negative 3 times 2 is negative 6. A squared times a is a cubed. Remember, all we're doing is adding our exponents. And then here, negative 3a squared times negative 1 will give you a positive 3a squared. All right, questions? Any questions? Next one, x minus 7 times x plus 2. So we have two binomials, and we need to do our binomial distribution. First, we'll do x times x. That's x squared. Then x times 2 is 2x. Negative 7 times x, negative 7x. Negative 7 times 2 is negative 14. All right, so we have this expression now. Combine your like terms, 2x and negative 7x is negative 5x. And that's the simplest way of expressing your answer. Any questions?
No, sir.
All right. So here we have y minus 2 times 3y squared plus y minus 5. So just like we did our distribution with two terms, We need to do the same thing with 3 terms, or 2 and 3. We have 2 terms in the first parentheses, 3 in the second. So we'll take the y, distribute it to each term, take the -2, distribute to each term. All right, so y times 3y squared is 3y cubed. Y times y is y squared. Then y times -5 is -5y. Then we have -2 times 3y squared, 6y squared. -2 times y is -2y. Then -2 times -5 is a +10. From there, combine your like terms. 3y cubed didn't have another y cubed to combine with. Then you have y squared and -6y squared, which is -5y squared. And -5y, -2y, it's -7y. Oh, also this 10 back here didn't have anything to combine with, so just bring it down. Any problems?
No, sir.
All right. So here, I'm gonna multiply what they call conjugates together. So when you have the same terms, the only difference is the middle sign. That creates a certain scenario that will always occur. And so in other words, if you the only difference between these two is the plus and minus in between. So when you distribute those, 2x times 2x is 4x squared. 2x times -3 is -6x. 3 times 2x, +6x. And then 3 times -3 is -9. So notice we have +6x and -6x in the middle. They cancel. That will always be the case whenever you're dealing with conjugates. Your middle terms will cancel. And that will leave you with 4x squared minus 9. All right, any problems? All right, so the next one. 1/2 x plus 6, 1/2 x minus 6. So just like before, we're going to do our binomial distribution. Don't let the fact that we have fractions, throw you off. You follow the same procedure. That'll be 1/2 times 1/2, 1/2 times 6, 6 times 1/2, 6 times 6. So right here, 1/2 times 1/2, all you do is multiply across, and that should give you 1/4. So that's how we got 1/4 x squared. So 1/2 times 1/2, and then x times x. And then the middle terms, 1/2 times 6. So that's just multiplied across as well. So you get 6/2, which is 3. Or in other words, half of 6 is 3. Same thing. So that's how we got 3x minus 3x in the middle. Well, -3x plus 3x in the middle. You did 1/2 times -6, and then 6 times 1/2. And then the last term, 6 times 6, gives that -6. Middle terms cancel. That leaves us with 1/4 x squared minus 36. Any questions? All right, 3w minus 4 squared is the same thing as 3w minus 4 times 3w minus 4. Make sure you do not square each term. That's not how you do that. You can't square them individually. You will miss a term if you do that. So you have to expand it out, 3w minus 4 times 3w minus 4, and then do your binomial distribution. 3w times 3w, 9w squared. 3w times negative 4, negative 12w. Negative 4 times 3w, negative 12w. Then negative 4 times negative 4, positive 16. And negative 12w and negative 12w will give you negative 24w. Binding your like terms. Questions? Any questions? So the next one is just addressing that similar scenario at least one more time. 5x squared plus 2 squared. So once again, you expand it out. 5x squared plus 2 times 5x squared plus 2. Then you have to do your binomial distribution. So 5x squared times 5x squared is 25x to the 4th. 5x squared times 2 is 10x squared. 2 times 5x squared is 10x squared. And then 2 times 2 is 4. Combine like terms in the middle. 10x squared will be 20x squared. Questions? Any questions? All right, so that's it for multiplying polynomials. Everybody good before we go to the next one? I believe that's the last section of chapter 12. Yep, 12.5. All right, so going back to a few more exponent rules, 12.5 is our negative exponents and scientific notation, but I don't think they go into scientific notation. Oh, yeah, we do. Okay, I was thinking about another class. Okay. Sorry about that. So, introduced these rules to you before, but we never did any examples with them. So we're going to do examples with them now. So a to the negative nth power is 1 over a to the n if you want to write it with a positive exponent. And then 1 over a to the negative n, if I want to write it positive, I bring it up to my numerator. So once again, let me say it like this, if it's in your numerator, you want to make it positive, bring it down to your denominator. If it's in your denominator, you want to write it positive, bring it up to your numerator. So that's how we're looking at that. And then if you have a fraction that's affected by a negative exponent, you can just flip it in order to have a positive exponent. And that's just the combination of both of these first two rules. You know, if it's in your denominator, take it to your numerator for it to be positive. If it's in your numerator, bring it down to your denominator in order for it to be positive.
So always make it a positive before we get going, right?
Yep, that'll be your best practice. Yep. Mhm. All right, so the directions would be simplify and then write, you talk about your final answer, write using a positive exponent. So in the first, we have 3 to the negative second power. To write a positive, you bring it down to your denominator. So we have 1 over 3 squared. 3 squared is 9. Next one, make sure you're careful. In the blue, I showed you another scenario in which would be a contrast to what we're doing here. So when we look at x to the negative 2, x to the negative third power, because there is no parentheses, that negative 3 is only applied to the x. So if I want to write it as a positive exponent, the only thing that's dropping down to my denominator is the x. If I wanted that exponent to affect both terms, then that's where this one comes into place. I would have had to put parentheses around the 2 and the x. And then that makes the 2x drop down to your denominator. So make sure you taking note of when you have parentheses and when you don't. If you don't have parentheses, then the only thing that's affected by the exponent is right up against it. And everything else is not affected by it. So. Any questions on those first two? All right. Next one, 2 to the negative first power plus 2 to the plus 4 to the negative first power. I can rewrite both of those as fractions. Drop the 2 down, and then drop the 4 down. So that gives me 1 over 2 plus 1 over 4. But if you want to add or subtract fractions, don't forget you need your LCD. That's the smallest number that each denominator can divide into evenly. So I decided that was 4 here. Didn't need to change the second fraction because 4 is already that denominator. But then here I have 2. So you ask yourself what times 2 will give me 4. That is 2. So you multiply top and bottom by 2. So that's 2 over 4 now as a fraction for that first one, and then plus 1 over 4. Have common denominators, add your numerators, and your final answer is 3 over 4. All right, any questions?
Can you slow down for a second, Mr. Tucker? Just on this section right here with this LCD thing.
Yep, not a problem.
Thank you. Thank you.
Yeah, not a problem. Not a problem at all. Any other questions before we go up? All right, so for the next one, we had 1 over 3 to the negative 4th. So this time our negative exponent is down in our denominator, so we needed to bring it up to the numerator. So that's why we have 3 to the 4th now. And then 3 times itself 4 times. It's going to be 81. All right. And this one, p to the negative fourth power over q to the negative fifth power. So all we have to do is flip them to write it positive. All right, so here we have x over x to the negative second power. Now we want to simplify this, not just rewrite it. We have x divided by x to the negative 2. Don't forget, whenever you're dividing your variables, you're going to subtract your exponents. Division always tells us to subtract our exponents. Now, you're talking about same variables. Both of them have x in it, so we're subtracting our exponents. Don't forget, when you don't see anything, that there's a 1 there for the exponent. So we have 1 minus negative 2. And the result would be x cubed. Negative 2, negative turns positive, so that's 1 plus 2. So that'd be x cubed. All right, any problems? All right, next one, a to the negative fifth over a to the seventh. Once again, we're dividing, so we're going to subtract our exponents. And so that's negative 5 minus 7, which would be negative 12. Then you can rewrite that as 1 over a to the 12th. All right. Okay. Just pull up. All right. So here we have y cubed z to the 6 raised to the negative 6 power. So that negative 6 as your power needs to be applied to each one of those variables. So that's why we have y to the negative third raised to the negative 6 times z to the 6 raised to the negative 6. So don't forget, when you're raising a power to a power, you're going to multiply your exponents. So negative 3 times negative 6 is positive 18 for y. And 6, well, negative 6 times 6 is going to be negative 36 for z. And then to rewrite that positively, or as a positive exponent, you drop the z to the 36 down to your denominator. Any problems? Any problems? Let's scroll up. Everybody okay? All right. So this next one, -2x cubed y over x, y to the negative first power. Oh, raised to the third power. We got a third power sitting on the outside. So what I would do is simplify as much as possible on the inside of the parentheses first before I go to that y cubed, not to y cubed, not before I go to the exponent of 3 that's sitting on the outside. All right. So first thing we can do is simplify our x variables and our y variables. Once again, we are dividing. So that means we're going to subtract our exponents. That's what I did over here. So the -2 hasn't been affected by anything yet. But then you have x to the 3 minus 1 for your exponents. And then y to the 1 minus -1 for your exponent. All right, any problems so far? All right, so simplify those exponents. Let me see. So 3 minus 1 is 2. 1 minus -1 is 2 because -2 turns positive. So you have -2x squared, y squared. Now that 3 needs to be applied to each piece of your term. So you have -2 cubed, x squared cubed, y squared cubed. So -2 cubed is -2 times -2 times -2, which will be -8. And then don't forget, whenever you have a power raised to another power, you have to multiply your exponents. So 2 times 3 is 6 for both of our exponents. Questions? Any questions? Let me scroll up. Pretty good. All right. So the last thing out of this section is scientific notation. Make sure you try, this stuff out. See if you have any questions on simplifying them. Every day is the opportunity for questions. So, when I end my lecture, I try to leave room at the end of the lecture so that you guys can ask the questions that you have. So make sure, you get those questions out there if you have them. If you don't, everything's well, everything's fine. All right. So last thing out of this section, and if I'm not mistaken, last thing out of chapter 12. Yep. So scientific notation is used to express very extreme values. So whether very, very small or very, very large, scientific notation is used for that. So it is written in the form of a times 10 to the r power. A is going to be in between 1 and 10. And R is an integer. So now A can be equal to 1, but it cannot be equal to 10. And R cannot be a decimal or fraction. It has to be an integer. All right. Here are just examples of how your interval, not interval notation, how scientific notation can look. 1.23 times 10 to the fifth power. So notice 1.23 is in between 1 and 10. And then your R, your exponent, is 5. Then you have 7.8 times 10 to the negative 31st power. Once again, 7.8 is in between 1 and 10. And then your exponent is negative 31. All right. All right, so we're going to write each number in scientific notation. So we have 367 million. First thing you want to do is find your decimal, and then we want to move it into a place that creates a number in between 1 and 10. So in other words, notice I put my decimal in between 3 and 6. It gives me 3.67. So that's in between 1 and 10. If I had put my decimal here, that would have been 36.7, which is greater than 10. So you're talking about putting the decimal in a place in between 1 and 10. So I took my decimal and placed it once again in between 3 and 6. That gives me 3.67. And it was 8 spaces to the left that I did that with. So you're talking about 1, 2, 3, 4, 5, 6, 7, 8. So I took my decimal 8 places to the left. And that's my result, 3.67 times 10 to the 8th. So that 8 goes, right here for your exponent. So it's going to be a positive move. And, whatever way you decide to rationalize when you use a positive number versus a negative number, you think about it like this: we had a very large number. So this exponent needs to be positive because it has to reflect. This number has to be that number right there. So if you break it down to 3.67, then you have to have a positive effect on 3.67 to make it that large. So once again, I have a large number, so I should have a positive exponent right here. So if I have a small number, then my exponent should be negative. So when we look at this, 0.000005, my exponent should be negative when I write it in scientific notation. So once again, it's all about first establishing what is your number going to be that's going to be in between 1 and 10. This time I move my decimal 6 places to the right to give me the number 5. And that'll be 5 times 10 to the negative 6. So that 6 goes right here. And once again, it was a small number, so I'm going to have a negative exponent. Check. Oh, that's just for a question. Okay. All right. Any questions on A and B before we go to C? All right, same type of deal. 20500000000. So if you don't see a decimal, it's to the right of your rightmost digit. And so we need to put that decimal behind the 2. That's going to be a number in between 1 and 10. So I end up moving my decimal 10 places to the left. So that's 2.05. And that'll be 10 to the 10th power. Questions? Any questions? Make sure we're all right. All right, so this in the chat. Oh, still talking about that question. Okay. Make sure we get that before we leave. All right, D, same principle, same process, creating that number that's in between 1 and 10. So we have 0.0085. So take that number 4 places to the right, 8.5, and then that's going to be 10 to the negative 4th power. All right. Problems, any problems? All right, so let's go the other direction. So write using standard notation without exponents. So this time we just reversing the process. It's a positive 5 on a exponent. We have 1.02. So we take the decimal that we see, move it 5 places to the right, and that's 102,000. So because it's 5, that means this number needs to be a large number when we finish. I mean, when I say 5, positive 5, because it's a positive 5, this number needs to be a large number when we finish. So if you were to take it to the left, it's going to give you a small number. So we need to take this to the right. Once again, reversing the process that we just did. All right. Here, 7.358 times 10 to the negative 3rd power. This time we have a small number. Or in other words, we have a negative, so we're moving our decimal 3 places to the left. 0.007358. And people always ask about the 0 to the left of your decimal. Is not necessarily, you don't necessarily, you don't necessarily have to have it. I'm used to putting it, but you don't necessarily have to have it. Any problems, any problems? All right, 8.4 times 10 to the 7th. This time we're moving it to 7 places to the right. 84 million. Pretty good. Last one like this. 3.007 times 10 to the -5 or -5th. Move your decimal 5 places to the left. 0.00003007 as our answer. All right. And that's it for that section. Questions on anything? Any questions? Everybody good? Everybody straight? Oh yeah, that's right. We do have a question in the chat. So determine whether each ordered pair is a solution of the given linear equation. And it says x equal to -3. How would I go about this? Can you answer the class? Okay. So before I go into your classmates' question, anybody have any questions about what we talked about? This is a question from a previous section. So everybody good with what we talked about?
Sir.
Okay. Yes. Oh, you said no, sir. Okay, cool, cool. All right. So let me get this right. So all right, Davon. I hope I'm saying it right. Let me know if I wrote down anything incorrectly. But we have determined if the order pair is a solution of, we have this equation right here, x equal to -7. And we want to know if these 3 order pairs, if either one of them are solutions. So now notice this doesn't have a y, it's just x equal to -7. So that's a vertical line for us at -7. And remember what that says is that y can be anything, but x is always -7. So whenever you have one like that, that's what that states. Same thing as if that was y equals to -7. That means x can be anything, but y is always going to be -7. So when you don't have both variables as a part of your equation, whatever that variable is, the other variable can be anything, but that variable that's in the equation is that number and will always be that. So once again, we have x equal to -7. That means y can be anything, but x has to be -7. So when we look at these three options as solutions, this one doesn't fit that standard because the y is -7. But what we need is for x to be -7. So that first one is not a solution, but these two are. So that one didn't call for any type of calculation. Just pretty much, it was conceptual because there's nothing to plug in. It's just recognizing that x is equal to -7, y can be anything. So as long as your ordered pairs fit that description, then they will be solutions. All right. Hopefully that helped out, sir. Let me know if not. All right. Any other math questions before we close out? I know somebody had to talk to me after class, but I wasn't sure if that was I think it was Joshua. I don't know if that was a math question or not. If it's not a math question, you can hold off for a second. Just want to see if anybody have any other math questions. It would be the same as saying, yeah, -7, yes. Mm-hmm. Yep. All right. So if you don't have any other questions, everybody's good. Like I said, I got to stay back, talk to your class, talk to a classmate or two. That's it for lecture. You guys have a good one. Be safe, and I will talk to you next class. Not a problem, sir. Not a problem. Have a good one. Thank you for the question.
You have a good one.
Thank you. You take
Great day.
care.
Thank you.
All right. Have a good one. All right, Mr. Holmes, what you got for me? Oh, wait, hold on. Do I need to, let me stop. It's not a math question, right?
Oh, it's more of like a personal kind of
Okay,
question.
yeah, let me stop the recording.
Yeah.